So as the name suggests, reduction of order is used to solve a higher order equation by reducing it to a lower order. And we are going to simply consider a second order equation, a linear equation, and reduce it to a first order equation. There are a bunch of steps that are involved in getting the solution by reducing the order. So let's first consider a second order linear differential equation. And we know that it can be defined as a2x y double prime plus a1x y prime plus a naught x y equals some function g of x. And we have this second order linear dE, and we can reduce it to a first order dE provided we know a solution. So suppose y1 of x is a solution to the dE. The goal is to find the second solution. Which would be y2 of x. So how do we go about doing this? We know that if y1 of x is a solution and y2 of x is another solution, then their ratio is not going to be a constant, provided they are linearly independent. Some function u is the ratio of y1 of x divided by y2 of x. So since we have that relationship, we could also write it as u equals y2 of x divided by y1 of x. That would also hold. So we're going to write it that way so that we can derive the relationship by reducing the order. So we have, excuse me, we have y2 is equal to y1 times u. I'm going to take the original dE and divide by a2 of x on both sides. And I could call the second term as p prime and q times y. For the purposes of reduction of order, we want g of x to be 0. In other words, we need a homogeneous second order linear dE. So we know that y1 is a solution. So we could find y2 prime and y2 double prime. So now y2 is equal to u times y1, y2 prime, if we use product rule, would become u y1 prime plus y1 u prime. y2 double prime would simply be equal to u y1 double prime plus y1 prime u prime plus y1 u double prime plus u prime y1 prime. Those two terms are identical, so I can combine them. Now, since y2 is a solution, it would satisfy the differential equation. We've seen this time and time again. So I'm going to take y2 and plug it in the original dE. So I'd have u y1 double prime plus u 2u prime y1 prime plus y1 u double prime plus p times u y1 prime plus y1 u prime plus q times y, which is u times y1, equals 0. So u y1 double prime plus 2u prime y1 prime, y1 u double prime plus p u y1 prime plus p y1 u prime plus q u y1 equals 0. I am going to combine that term, and that term together. So I would have u y1 prime plus pu y1 prime plus qu y1 plus 2u prime y1 prime plus y1 u double prime plus, excuse me, p y1 u prime equals 0. Since y1 is a solution, if I pull the u out, I would have y1 prime plus p y1 prime plus q y1 plus 2u prime y1 prime plus y1 u double prime plus p y1 u prime equals 0. Now, that term would become 0 because we know that is true, and y1 is a solution, so when I plug in y1 here, it must become 0. So that would imply u times 0 plus 2u prime y1 prime plus y1 u double prime plus p y1 u prime would be equal to 0. So we reduce it and have it to this form. And still, it looks like a second order differential equation. So if I let, say, w equals u prime, then y1 w prime would be equal to y1 u double prime. Because w is u prime. And we would have p y1 w plus 2w y1 prime equals 0. If I rewrote this, I could divide by y1 on both sides. So the y1s would go away, and I'd simply have w prime plus p times w plus 2w y1 prime equals 0. And w prime, I could rewrite it as dw over w, and p times w would simply be p times w as is, and 2 times w times dy over dx would equal 0. dy or dy1. Let's see if we can gather things together. I have to divide by w also. I skipped one step here. So if I divide by w on both sides, I'd have w prime divided by w plus pw over w plus 2y1 prime divided by w equals 0 divided by w. So that would give me w prime plus p plus 2y1 prime equals dx. 0. Now we know that w prime is simply dw over dx. And p, and 2 times y1 prime, I could write it as dy1 over dx. If I multiply by dx on both sides, I would end up getting dw over w plus p times dx plus 2 times dy1 equals 0. I can move that p times dx to the other side. I feel like I'm missing y1. Yes, I am. So there is a y1 here, which I missed right there. So I'm going to insert it. So y1, 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 y1. And now I'm going to integrate on both sides. So integral of dw over w plus 2 times integral dy1 over y1 equals integral minus p dx. And when we integrate it, we are going to get a constant. So the first integral would reduce to ln of w, second to ln of y1 equals negative integral p dx plus c. Using algebra, I could combine these two and write it as ln of w plus ln of y1 squared equals negative integral p dx plus c. Using the properties of logarithm, I could rewrite that as w times y1 squared ln equals negative p dx plus c. Take exponential on both sides. The e and ln would go away, so we would have w y1 squared equal to e raised minus integral p dx times e raised c. But e raised c is a constant, so I could rewrite it as w times y1 squared equals e raised minus integral p dx, the constant c1. Now we've got defined u, because u is going to give us w. So what we have just found is w y1 squared equals e raised negative p dx times c1. If I divide it by y1 squared, and substitute w as u prime, I would get that expression. So now we have to integrate on both sides. So if we integrate on both sides, we would have integral u prime equals integral e raised negative p dx divided by y1 squared, multiplied by the constant c1, and we would get another constant c2. So integral of u prime is simply u, and that would equal to e raised negative integral p dx divided by y1 squared times c1 plus c2. So we've found the solution for u. Now that we have a solution for u, we have to find the second solution, which is y2. Since u is equal to, y2 is equal to u times y1 from earlier, just right here. I'm going to plug in the u that we just derived. So y2 would be equal to y1 integral e raised negative integral p dx divided by y1 squared c1 plus c2. For convenience, we're going to set c1 as 1 and c2 as 0, which would give us the second solution, y2 equals y1 integral e raised negative p dx divided by y1 squared, and that would be the solution, or the second solution that we are looking for. So it's a lengthy process, but typically what we have to do is find the value of p, and once we find p, we just have to plug it in that formula, and we can readily get the answer, y2. So where did the reduction of order happen? When doing all these substitutions, I eventually ended up with an equation which is right here. And that is a first order dE in W. So we have reduced a second order dE to a first order dE, hence the name reduction of order. And the key formula is right here. And that's what we're going to use to find the second solution. So here is a second order homogeneous dE, y double prime minus 4y prime plus 4y equals 0. We know one of the solutions is y1 equals e raised to x. So we just have to find what p is. Based on how we defined things, p is simply negative 4. I'm making a direct comparison to that equation right there. Now y2 would then be equal to y1 integral e raised negative integral p dx divided by y1 squared. So y2 would equal e raised to x integral e raised negative 4x divided by e raised 2x squared and dx. y2 would then be equal to e raised to x, and if we pull the negative 4 out, that has to be dx. And use the property of exponents, the denominator would become e raised positive 4x. So the numerator is e raised negative 4x divided by e raised positive 4x multiplied by dx. So that would equal to e raised to x integral e raised negative 8x dx. The integral of negative 8x is e raised negative 8x divided by negative 8. Using properties of exponents, we'd have e raised negative 6x divided by negative 8. And that would be the second solution. Keep in mind that this second solution is not going to have constants. If we have to find a general solution to the DE, a linear combination would form a family of solutions. So note the general solution is y equals some constant c1 multiplied by y1 of x plus some constant c2 multiplied by y2 of x. And they are linearly independent, so we could write it as c1 e raised to x plus c2 times e raised negative 6x over negative 8, which we can further write it as c2 over negative 8 times e raised negative 6x. Constant divided by negative 8 is still a constant, so I could call that as c3. So the final general solution, which contains arbitrary constants, is c1 e raised to x plus c3, sum of the constants multiplied by e raised minus 6x. And that is the general solution. Keep in mind we don't have a particular solution because this is a homogeneous equation. So the right hand side is 0. So here is another second order equation. The right hand side is 0, but the leading coefficient here is 9. So we have to rewrite it as y double prime minus 12 over 9 y prime plus 4 over 9 y equals 0, which would reduce to y double prime minus 4 over 3 y prime plus 4 over 9 y equals 0. And based on our derivation, if we make a direct comparison to y double prime plus py prime plus q equals 0, we would identify p to be negative 4 over 3. So now we could put it in the formula. y2 is equal to y1 integral e raised negative integral p dx divided by y1 squared dx. And a common mistake is I've seen students make is cancel this y1 and y1 squared. You cannot do that. If you go back and look at the derivation, that y1 stayed outside of the integral. So you can't simply cancel them out. So don't do that. So y2 would equal to y1, it is the given solution, e raised to x over 3, integral e raised negative integral negative 4 over 3 dx divided by y1 squared e raised to x over 3 squared dx. So we have e raised to x divided by 3 integral e raised positive 4 over 3 integral dx over e raised 4x over 3 dx. So e raised to x divided by 3, integral, the numerator is simply 4 over 3x, denominator is 4 over 3x, multiplied by dx. So those two would get cancelled, and we would have e raised to x over 3 times integral dx. So we would end up having e raised to x over 3 times x. If we have to write a general solution, I just want to double check that everything is in place. Yes. Some constant c1 multiplied by y1x plus some constant c2 multiplied by y2x, c1 e raised to x over 3 plus c2 x times e raised to x over 3. We have 2x over 3 in common, so the solution would be c1 plus x c2. So here is another equation. So there is a mistake here. I forget. Let me check one time. Okay, so the mistake here is x squared y. So the first thing is to divide the equation by x squared on both sides. So y double prime minus x over x squared y prime plus 2 over x squared y equals 0, which would imply y double prime minus 1 over x y prime plus 2 over x squared y equals 0. By direct comparison to our derivation, we have y double prime py prime plus qy equals 0. If you noticed by now, you could see that q doesn't play a role at all based on our derivation. So it really doesn't matter what q is in finding this second solution. So p ends up being negative 1 over x. And the second solution would be y2 equals y1 integral e raised negative integral p dx divided by y1 squared dx. So y2 would equal to y1, and y1 is our solution that is given in the problem right here. So x sine ln of x integral e raised negative 1 over x dx divided by y1 squared, which would simply be x squared sine ln of x squared dx. So that would give us x times sine ln of x integral e raise the negatives. If you multiply, we would simply get dx over x and dx over x in the numerator would simply be equal to ln of x those two would go away and we would simply have x times sine ln of x multiplied by x over x squared sine squared ln of x dx. So y2 is equal to x times sine ln of x integral 1 over sine squared ln of x multiplied by dx over x. And you may say, well, how are we going to integrate this? Well, if we substitute u is equal to, well, let me call it a different variable. V equals ln of x. dv is 1 over x dx. So x times sine ln of x integral 1 over sine squared u du but 1 over sine squared u du is simply cosecant squared u du, and we know the integral of cosecant squared x is simply cotangent x, or in this case cotangent u with a negative. Plugging cotangent u back in terms of sine and cosine, we would have cotangent of ln of x negative sine or x times sine ln of x. Replace cotangent ln of x, we have cosine ln of x divided by sine ln of x. Those two terms would go away. We have negative x cosine ln of x. So the second solution is simply negative x cosine ln of x. The first solution is x times sine ln of x. So the general solution is y equals c1 y1 of x plus c2 y2 of x. So we have c1 x sine ln of x plus c2 negative x sine ln of x. Oops, sorry. Negative x times cosine ln of x. We have an x in common, so if I pull x out, I have c1 sine ln of x minus c2 cosine ln of x. And that is the general solution.